Welcome to our sub-day intro here. I wanted to give some help with this one. The factors that affect how much each of these types of energy something has. So gravitational energy, our equation is Eg equals mgh. So the factors that affect it are mass and g is 9.8 meters per second squared. That's just the units. G is the acceleration due to gravity. So things accelerate at 9.8 here on Earth. It'll always be 9.8 on Earth unless I ask you to do a problem about the moon or some other planet. And the last one, the most important one in some ways, is the h, the height, is the other factor. For kinetic energy, the equation is 1/2 mv squared. So the factors that affect it are the mass and the velocity, right? The variables from the problem are from the equation are the factors that affect it. And for thermal energy, what are some factors that affect it? Friction is our main source of thermal energy in most of the situations that we're talking about. You could also make thermal energy from sound or other vibrations. That's what would go into thermal energy. So describe the energy of a bouncing ball using these energy terms. So a ball held away from the ground has Eg, so I've used one of my terms, right? When we drop it, the Eg, does it transfer or transforms? It's one ball, so it transforms into Ek. We've got another of our terms down, two more actually. These are all good to go. And I don't know why that didn't strike those through. When we drop it, the Eg transforms into Ek. Okay? Then, when it hits the ground, what happens? The Ek transforms into E elastic, right? That's our elastic energy. And that's what's going to allow it to bounce back up. So the Ek transforms into E elastic and transfers some of its energy to sound and heat because of the contact. Then the E elastic transforms back into Ek, kinetic energy, and then because it's got kinetic energy, as the ball rises, the Ek transforms back into Eg, and the whole process starts over again. Okay, so then I look back up here, and I see I've used all of my terms now except thermal and total. So I'm going to change this heat into sound and E thermal so that I use my term, right? It always helps to use the proper term, and maybe I should just copy paste this. That's a good way to do it. Oh, not really, but that's okay. And we haven't used E total. So throughout this time, E total remains the same. And I don't know why I didn't copy the cell that time. But that's the idea there. That's the sentences that you're looking for. There's a lot of variations on the way that you could phrase this, but this is the general idea. All right, now we've got the sled here, and it's rolling down the hill. The arrows indicate how fast the sled is moving. The arrow size has to do with how fast it's going. So here at position 1, I've given you all this information, so we can just add these up. Total energy is the three energies added together. So total joules of 20 joules of total energy. And I did mess up here when I gave this to you. These should all have joule measurements in the top column. All right, and then down here, I gave you a hint. Position 2 is halfway down the hill. That means the Eg will have cut in half. And then I have another gap here that I want to fill in, and I have two gaps. But I know this one, don't I? E total remains the same. If you do not get this conservation of energy idea, many of these problems will be impossible for you on the test, because there's no other way to know what this is unless you know this one. So this must be a 9 here, right? We've got to add up to 20. And then at the bottom of the hill, the EG is 0, right? It's at the bottom of the hill. It can't have any more potential energy. And so the rest of the energy must be kinetic. All right, and then position 4 is back at that same height as 2. They're on the same level, so it must have the same EG. And the EK isn't 9, though, because we've given more of our energy to heat. And so our EK must be 5. And finally here, our EK has to be 6, so that these all add up to 20. Thanks for watching.